Welcome back, everybody. Today, we are going to start looking into something called potential energy diagrams. So what we talked about last time, the whole kinetics thing and collision theory, we were talking about how the reactants have to smash together with enough kinetic energy in order to break apart and form this really high energy thing called the activated complex, and usually they snap back together to form the products. And something that I want us to look at to help us kind of like see what's happening and like really get a better understanding of what's going on in a chemical reaction are these things called potential energy diagrams. And what they do, well, actually I should say what it is basically just a graph of the potential energy of our things as we go through the chemical reaction. And it helps us follow the energy, because energy is like an elusive little thing. It can change instantly from one form to the other, and it can come and it can go, and it can look like it vanishes or comes out of nowhere, but it's not magical. It's a thing that's like, it doesn't magically appear or disappear, but it's kind of hard to keep track of. So what we're going to look at today are potential energy diagrams in order to help us to understand what's happening with the energy during a chemical change. I hope that makes sense, and because that will also help us understand the one step further, getting to this thing called equilibrium. So let's just dig right into it, guys. These things called potential energy diagrams. Okay, so as the reactants collide, like I said before, their kinetic energy is turned into potential energy, right? So you have reactants, they're just like kicking along, and all of a sudden, bam, they smash into each other. And what happens is kinetic energy is transformed instantly into potential energy. Right? And then at the peak of that energy is where we say we have the activated complex, and from that activated complex, the products form. Got it? Okay, so this is the potential energy diagram. And like I said, it helps us kind of keep track of what's going on with the energy so we can get a better understanding of what's happening inside the reaction. And so, like over here, right, here we have our reactants. They're just chilling. They're just sitting around minding their own business, and their collective potential energy is here on the scale. Now, typically, these diagrams have no numbers because they're generic, because they work for like every reaction. You just have to, it's just these numbers are different. So the reactants are here. Let's use a pretend number of 10 joules of energy, I don't know, whatever. And so, blah, 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 they're minding their own business, and then smash, they crash into each other, and all that kinetic energy, right, kinetic energy, which is, like thermal energy, is converted into potential energy as they collide, and the force of their motion is like put into this explosion of broken bonds and broken up molecules. And here at the very tippy top, at the apex of the potential energy, we have the activated complex. And I'm just going to draw this over here so I can keep track of where I am at the scale. Let's call this 12. I don't know why. There you go. Yeah, so the system gains potential energy, and then if we're lucky, if it collides hard enough to break all those bonds, which it looks like it because it says right here activated complex, right? So if that's the case, it explodes, it makes the activated complex, and we're going to pretend like it had the proper spatial orientation. So everything links up together and it falls down, boop, it makes these things, things that we're looking for, the products. Now the potential energy of the products, let me just do a dotted line here so I can see where I am on the scale. I don't know, let's keep the math easy. 2, right? So in all, right, the different, like we went from here, we dropped down to here, and we lost 8 joules of energy, right? But we needed 2 joules of energy. So this is the activation energy, right? Because it's the energy it takes to like make the activated complex, to get that thing started. So we had to go from this level on the scale, we had to go up to here, to this level on the scale. Does that make sense? And then this different here, let me draw another dotted line here just to keep track of our scale. If I went from here to here, right, like we started here, we dropped down here, that's 8 joules, that's the amount of heat that came out of this reaction. So this is like how exothermic it is. Does that make sense? I hope so. And the way things work here, this is like the left and right, like the horizontal, that's what we call the reaction coordinate. This is forward going this way, and that way is going reverse. And this is just a scale of potential energy. Now, like I said, usually when you see these, there's very rarely like a scale on the side because we try to keep it generic so it works for like every single like reaction that you could think of. Nice. So most reactions, like at least the ones that we're going to be looking at, the energy that is absorbed and released is almost always in the form of heat. Okay? Because like we said, like they're moving up over here, the reactants, and then all of a sudden their kinetic energy is turned into potential energy. Now, kinetic energy, if you remember, temperature is the measure of the average kinetic energy. So, like, kinetic energy is really closely related. It's basically your thermal energy, as far as we're concerned here. So that energy of motion, that's like heat energy, basically, and right, and so that all gets converted into potential energy. And when it comes out, when that energy is released, it is released in the form of heat. Just like when you're burning firewood, the energy that is released is like in the form of heat, and we call it delta H, or enthalpy, or heat of reaction. So this thing actually has 3 different names, because why wouldn't we, right? So in this case, the delta H would be 8 because it's the difference from reactants and products, right? And that word it was being released. So in these chemical reactions that we are going to be looking at, the energy absorbed and released is going to be in the form of heat energy, right? Like matches, candles, Bunsen burners, right? All these chemical reactions that we're really familiar with, they give out heat. Got it? Awesome. Now, 3 names, let's not forget. So if delta H, this thing, like the amount of heat that is released or absorbed, so it can go both ways. It can be taken in and it can be spit out, right? So if it is exiting, remember this term exothermic? Exo means exiting, right? So if it's exiting thermic or exiting heat, right? So exo is like exit, thermic is heat. Like it's heat is exiting, right? And if that's the case, our delta H is going to be negative. Just like if you were making a withdrawal in your bank account, like it would show up as a negative, as like money leaving your account. Well, in a chemical reaction, if heat leaves, it will be negative because heat is leaving the reactants, right? And so if we touch something that is exothermic, it's going to feel hot. Actually, let me back up and clarify that for a minute. If we touch a chemical reaction that is hot, which is much different than a phase change, right? So it has to, I'm talking specifically about a chemical change here. If a chemical change or a chemical reaction gets warm or feels hot, that is exothermic because heat is leaving the system. Totally different than phase change, which we talked about last chapter, right? And the reason why it feels hot, the reason why heat is escaping, is because the potential energy of the reactants, like where we start, is like up here, and the products, like where we end, is down here. So we started at a higher potential energy, and we ended at a lower potential energy. And all that the difference comes out in the form of heat. Does that make sense? Just like what we got right here in like cellular respiration. So for cellular respiration, you put in glucose and oxygen, and you get out carbon dioxide and water and energy. Dig? Awesome. Now, if we were to put that into a chemical formula, it would be the reactants, which in this case is sugar plus oxygen, is going to make CO2 plus water plus energy. Right? So energy is here. See how it's on the product side? It's like on the side of what is being produced. It's like what we're making. You guys picking that up? Super duper. Now the exact same thing, only completely opposite, would be photosynthesis. See, now photosynthesis is endothermic. Like, remember, En is for entering, and then thermic, heat. Heat is entering, right? So for this one, we have what do we have to put in here? We have to put in water and okay. So for this one, we have CO2 plus H2O plus light in the form of energy. We're going to make sugar plus O2, and that's what comes out. You dig? Right? So respiration, we can call that the forward reaction. And thank God we have photosynthesis for the reverse reaction of that. So, we can breathe and stuff. But in a regular old chemical reaction, if it is endothermic, if heat is being entered or put into the system, the delta H is going to be positive. Just like if you put a deposit into your bank account, it shows up as like a plus because your account is growing. It's entering, right? And for us, if we feel this chemical reaction, it'll actually feel cold to the touch because it is absorbing heat from its surroundings, and the temperature of our sample will get lower and lower and lower, which is pretty wild. But it happens. I mean, this is not something crazy. Like, I'm sure you guys have all seen those cold packs that they have in the nurse's office or whatever. Like, there's a bag inside of a bag. You crack it and shake it, and it gets kind of cold. Well, kind of. But that is an endothermic reaction. Dig? And it is endothermic because in this case, we're starting with the reactants here, low energy, and the products end up with high energy. So we start out low energy and we pack energy into that as we make our products. And then we have stored energy. It's also a lot like batteries. Like, exothermic is when batteries have a lot of stored energy, and then when the batteries are dead, that is exothermic. And then endothermic is when we charge those batteries. We go from low energy all the way up to back to high energy. Do you guys get what I'm saying? Certainly hope so. Moving right along, let's look at what these potential energy diagrams are going to look like, right? Okay, so if we have exothermic, right, that means that we're going to lose energy, right? So our reactants are going to have to start here, arbitrarily higher energy. And I know that once we're all done our reaction, our products are going to have low energy. However, if you recall, in order to make a chemical reaction happen, the reactants have to collide hard enough to break bonds and form that thing called the activated complex. And so the reactants have to gain energy high enough to make the activated complex. So boop, we're going to jump up like this, right? And this is where the activated complex lives. And then as soon as the activated complex is made, the potential energy drops down, energy is released. Yeah? So this is what exothermic looks like. The reactants are higher than the products. Now the same thing, only completely different is endothermic. And for endothermic, our products have to start out, our reactants have to start out low, and our products have to end up having higher energy. However, it is never going to be like this. Nope, it cannot be a straight line, okay? Because we have to form that thing called the activated complex, and pretty much no matter what, that activated complex is always going to be the highest energy situation in the entire process. So here's where the activated complex lives, and the reason being is because it's so super duper unstable that it always falls apart and forms something like less stable than the activated complex. So that's what exothermic and endothermic look like when we draw out the potential energy diagrams, right? And so from here we can get a couple of kind of energies, right? So let me get a line there. If going from reactant up to activated complex, and it doesn't matter if it's exothermic or endothermic, anytime you go from reactant up to the activated complex, that is your activation energy. Does that make sense? Because that's the energy you need to add to make the activated complex. Remember learning about enthalpy or heat energy? Right, so let me draw another line. Oops, I'm going to draw a straight line here and a straight line here, just so I can keep scale on our energy. Right? This energy, the energy difference between reactant and product, whether it is exothermic or endothermic, it really doesn't matter. The difference between reactant and product, we call that delta H, or the heat of energy, or heat of reaction, the enthalpy, if you will. Does that make sense? And there are a couple other things that we should look at. Oh wait. One other energy. Oh, you know what? We'll talk about that later. I don't want to get there right now. Yeah, here we go. Let's just keep moving on. I'm going to come back to those diagrams after I talk about this right quick. Because reactions don't always go in one direction. I will refer to you to this thing right here. Ooh, right there. See this guy? Right. Now let's look at that guy. Right? So you can make carbon dioxide and water into sugar and oxygen and sugar into carbon dioxide. It's reversible, right? So in certain conditions, reactions can go in the reverse direction. They can go both forward and reverse. And this is how we get this weird thing called equilibrium. Now, how does it happen? It happens if the products collide with enough energy and the proper spatial orientation and form the activated complex. So if they're lined up right and they have enough energy to create the activated complex, well, guess where you end up? You end up right here. And so it's possible to start at the products, make the activated complex, and land down where the reactants are. That is absolutely possible. And when that happens, we get a different kind of activation energy. Let me extend my lines for the scale over here. Now, for the reverse reaction, we're going to start at the products, right? Because reverse is going that way, right? So if I start at the products and I go all the way up to this point, this is going to be the activation energy, like from here to here, like this portion of the scale, whatever number that is, like final minus initial, just the difference between the two. That's going to be the activation energy for the reverse reaction. Do you guys dig what I'm saying? You all picking up what I'm putting down there? Certainly hope so. Same thing like over on the exothermic situation. If I start at the products and add enough energy to get all the way up to here, to where the activated complex lives, that's going to be the activation energy for the reverse reaction. Does that make sense? So we actually end up having two activation energies. We have activation energy for the forward reaction, and we have activation energy for the reverse. Over here, we have activation energy for the forward reaction, and here we have activation energy for the reverse reaction. If you notice, the forward reaction starts at the left and goes right. Yeah? Starts at the left and goes right. Yeah? Now the reverse starts on the right and goes left. The reverse starts on the right and goes left. See how that works like that? You dig? Awesome sauceum. That's actually great. And that is some trippy weird stuff, because now chemical reactions can go backwards. Simple. Just remember, activation energy for the forward reaction is when you're going forward, from left to right, and the activation energy for the reverse reaction is when you're going backwards, right? You know what I mean? From right to left. Awesome. So I also want to talk about enzymes and catalysts in potential energy diagrams. So here's a really quick, let's do exothermic potential energy diagram. See, generic, just like as generic as I can make it. However, if we add an enzyme or a catalyst, so in chemistry we call it a catalyst. In biology it's called an enzyme, because an enzyme is a catalyst specifically for biological processes. In chemistry we cover everything, it's everything. Chemistry is all of the sciences, so catalyst covers everything. So if we do add a catalyst, what happens is that instead of following this path, it gives it a new pathway. In other words, broken down on the molecular scale, it changes the reaction mechanism. By usually, like most enzymes and catalysts, hold things in place so the spatial orientation is sort of taken care of, right? So if you think about it, excuse me, if you go back to my analogy of keys, right? For a key to work a lock, it has to be lined up just right. Now the force to push a key into a lock, not that much, you know what I mean? However, if I stood here and threw my keys at the door, I would have to throw my keys many times, many times, before I threw it in such a way that the key lined up with the lock and popped right in, right? But an enzyme or a catalyst holds that key right in position so it just flies right in. So do you understand what I'm saying? That's what enzymes and catalysts do. They kind of hold things in place. And by doing that, what happens is the energy needed to make the activated complex is dropped. So you only need to go up like that. right? So before we had to get from here all the way up to here, right? However, when we added a catalyst, we only had to go there. So it lowers the energy of the activated complex. And each catalyst has its own like special way of doing that, but usually it helps hold things into place. Okay? So, here's the question is what changes with the addition of an enzyme or catalyst? We have where'd my thing go? There we are. We have a lower energy of the activated complex, right? So instead of being way up here, it is dropped all the way down to here. So it's here with a catalyst. And so if you'll notice, the energy of the activation energy is much smaller, right? And look at the energy, the activation energy for the reverse reaction, right? It is definitely smaller than it would be if we did not, if we did not have the catalyst, right? Let's go like that. So it lowers the energy of the activated complex, and in doing so, it goes faster both forward and reverse because they are both lowered by exactly that much. So it is exactly this much easier to go forward and reverse. Does that make sense to you guys? But other than that, other than the fact that it lowers the energy of the activated complex and both the forward and reverse reaction go faster, what else is the same? Like everything. If you'll notice, delta H, it still goes from here to about here, right? Like the reactants are still here and the products are still here. So there's not much else that changes. All it does is lower the activation and the energy of the activated complex. So what I want us to do now is to identify the following. So what I like to do with these, so what I'm going to do is I'm going to draw lines on here that represent the different potential energies. But I like to draw these lines here just so I can sort of keep track of like where the scale is. Okay? So for this first one, the potential energy of the reactants, tell you what, I'm going to use numbers, okay? So I'm going to call this number 1, potential energy of the reactants. So what is the total potential energy of the reactants? Well, it goes from the ground all the way up to where the reactants are, right? The next thing for number 2, the activation energy for the forward reaction. Well, how much energy do we need to activate the forward reaction? Well, forward reaction is going that way, right? From left to right. So I need to start at my reactants and I need to go all the way up to my activated complex. So I'm going to call that number 2. That's going to be the activation energy for the forward reaction. Now, potential energy for the activated complex. Well, we know the activated complex lives right here, right? So it'll be from the ground all the way up to here. That's the energy of the activated complex. Now the energy of the products, well, products live right here, right? So it'll be from the bottom all the way up to there. Oops, I forgot to give me number 3 here. All right, finally, well, actually not finally, let's look at numero 5, delta H. Well, delta H is always the difference between reactants and products. So I have to go from like here to here. I guess I'll draw it right here. There. There. That's delta H. This energy, right, the difference between reactants and products, that's my delta H, my enthalpy, my heat of reaction. Right. Nice. Okay, so let's see what other color. Oh, let's do this color. Activation energy for the reverse reaction. So reverse reaction, we're going that way. So I need to start here, and I need to get all the way up to the energy of the activated complex, which would be here. That's my number 6. You guys see how that works? There's 6 things here that we need to have. 6. And there are 3 things, and there are 3 energies. Okay, so the 3 things that we need to have are the energy of the reactants, the energy of the products, and the energy of the activated complex. Those are the 3 things that we need. And then there are 3 energies. We have activation energy for the forward reaction. We have activation energy for the reverse reaction. And then we have the energy or the heat that is released. So heat to start it forwards, heat to start it backwards, heat that comes either in or out, delta H. So 3 things, 3 energies. Got it? Great! Moving on! Here we go. Oh, identify. Oh, wait. Whoa. But you guys already do that. Not that easy. All right, let's do this one. Okay. So and now I'm gonna make it just a little bit more difficult. I'm gonna make it a little more. So I still need to have these lines. You'll see on the tests and quizzes that they include these lines here. And these dotted lines are just to, remember, are just to help us keep track of the scale. Usually they're actually drawn straight. Yeah, what are you going to do? And I'm going to draw some random lines, and y'all are going to tell me what they are. So I'm going to go... One, two, three, 4, 5, 6. Okay. Let's see if we can name these bad boys. Let's start with... number 1, potential energy of the reactants. So which one of these lines is the potential energy of the reactants? Well, first we got to find out where the reactants live. Remember, reactants are always here. Activated complex is always here. Products are always here. So any line that goes from the bottom all the way up to here. That one right there. Right? See how that arrow represents the energy, like how high up on the scale are the reactants right there. So number 2, activation energy for the forward. I always do that to make sure my eyes are going in the right direction because, you know, broken. So for the forward reaction, I'm going to start at my reactants and I'm going to pop all the way up to my activated complex. So I need to find a line that goes from here all the way up to here. Oh, there it is. It's right there. Oops. Yeah, that's going to be the activation energy for the forward reaction because it's the amount of energy I need to go from the reactants. The reactants are at this high on the energy scale, and the activated complex is this high on the energy scale. So there's my line number 2. How about line number 3? Potential energy of activated complex. Well, that's easy. Activated complex lives right here. So whoever goes, I need a line that goes from here, from 0 up to here. So this whole thing, oh, that's easy. That's this guy. Okay, number 4, potential energy of products. Well, that's just from 0 up to where the products are. Here are my products. Something from here to here, from bottom to the, oh, here it is. There's 4. 5, delta H. Remember, delta H is the difference between reactants and product. Oh, that's easy. I got it right here. So here are my reactants. Here are my products. My products are at this level, and that's this guy right here. And 6, activation energy for the reverse. Remember, we're going to go that way for reverse. So I'm going to start at my products and have to go all the way up to here. So I need a line that represents the difference between this energy and this energy, like whatever that is, like 10 and 12, whatever. And no, from here to here, from here to here. Ooh, there it is right there. Nice. Nice. So exothermic or endothermic? We're starting here. And we're ending way up here. That is so endothermic. That's like as endothermic as you can possibly get. That is crazy. Wait, no way. No way. Man. That was a lot. I'm not gonna lie. That today was a lot to like body slam onto you guys. But I ain't scared for you. I know y'all can do this. And so to practice these, to work on them, we are going to do two things. We have two practices: role of energy in reactions and interpreting reaction coordinates. Hold on tight, guys. We are gonna start cranking because we're just getting warmed up. All right. So I hope you guys have a super awesome day. I know I am, and I'll see you guys very soon. Okay? Have a good one.